Take a moment to picture your morning routine. Your alarm goes off precisely at 7 o'clock. You glance at your calendar to confirm today's date. You schedule meetings, catch trains, and plan your entire life around the steady, unwavering tick of modern timekeeping. But what if all of that vanished? What if every clock, every calendar, every digital device that tells you what time it is simply disappeared? How would you know when to plant your crops, when to celebrate the new year, or even when to meet a friend? This wasn't a hypothetical question for our ancestors, it was their everyday reality. Long before the invention of mechanical clocks or standardized time zones, ancient civilizations faced the immense challenge of measuring and making sense of time using only the world around them. And what they accomplished with nothing but observation, intuition, and ingenuity remains nothing short of breathtaking. From the moment human beings first looked up at the sky, we have been haunted and fascinated by the passage of time. The sun rose and set, the moon waxed and waned, seasons changed, generations passed, and the stars wheeled overhead in an endless, mysterious dance. For ancient peoples, time wasn't a number on a screen. It was written in stone, shadow, and celestial motion. It was felt in the warmth of the sun, seen in the length of a falling shadow, and heard in the rhythm of the tides. They didn't just want to know the time, they needed to. Survival, spirituality, agriculture, and society itself depended on it. And so, with patient dedication and remarkable creativity, they learned to read the heavens and the earth like a grand cosmic clock. This video is a journey back to those beginnings, to the very origins of how humanity first learned to capture and quantify time. We're going to explore the world's oldest and most ingenious timekeeping methods, from the obelisks of ancient Egypt that told time by the sun, to the intricate water clocks of China that measured hours through the steady drip of water. We'll see how the Maya tracked planetary cycles with staggering precision, and how cultures from Babylon to Britain built monuments that doubled as massive astronomical calendars. These weren't just practical tools, they were expressions of human curiosity, reverence, and an unshakable desire to find order in the chaos of existence. By the end of this exploration, you won't just understand how ancient civilizations kept time, you'll see the sky, the shadows, and the very turning of the earth in a completely new light. For these early cultures, the sun and moon were far more than distant lights in the sky, they were the very heartbeat of existence, the original timekeepers upon which all of life's rhythms depended. Without any technology to rely on, our ancestors turned their gaze upward, learning to read the subtle language of the heavens. The most obvious and essential cycle was the sun's daily journey. Its predictable arc from east to west provided the fundamental unit of time, the day. This solar rhythm dictated the structure of human activity, dividing time neatly into periods of light for work and hunting, and darkness for rest and safety. But the sun offered more than just a daily schedule. By carefully observing where it rose and set on the horizon throughout the year, ancient people could track the changing seasons. They noticed the sun's path shifted northward in the summer, bringing longer days and warmer weather, and southward in the winter, with shorter days and cold. This solar dance marked the perfect times for planting, harvesting, and migration, making it absolutely vital for survival. While the sun governed the day, the moon presided over a longer, more mysterious cycle. Its transformation from a thin sliver to a brilliant full disk and back again provided a beautifully clear, roughly 29.5-day calendar in the sky. This lunar cycle was incredibly easy to observe and track, making it one of humanity's first methods for measuring periods longer than a single day. Many early calendars were based primarily on these lunar months. The word month itself is derived from moon, a linguistic fossil hinting at this deep historical connection. People would count the days between each new moon or full moon, creating a reliable way to plan for events that required more than a daily outlook, such as ceremonial gatherings, trade meetings, or tracking pregnancy terms. The moon's influence extended beyond the practical, however. Its soft, silvery light illuminating the night landscape fundamentally altered what was possible after dark, influencing everything from nocturnal hunting strategies to the timing of storytelling and spiritual rituals under its glow. This intimate relationship with the cosmos fostered a profound sense of connection. The cycles of the sun and moon were not seen as cold, mechanical processes, but as living, powerful forces intertwined with the divine. Deities were often assigned to these celestial bodies, a sun god driving his chariot across the sky, a moon goddess governing fertility and the tides. This sacred connection meant that timekeeping was never a purely scientific endeavor. It was a spiritual act, a way of aligning human life with the will of the gods and the fundamental order of the universe. By observing and honoring these cycles, people believed they were participating in the cosmic balance, ensuring the sun would continue to rise and the seasons would continue to turn. This fusion of practical necessity and deep reverence is what transformed simple observation into the foundation of all ancient culture, laying the groundwork for the incredible innovations that would follow. Among the countless innovations born from watching the sky, one stands out for its elegant simplicity and enduring legacy: the sundial. This remarkable device transformed a simple, everyday observation, that shadows change position as the sun moves, into humanity's first dedicated timekeeping machine. The fundamental principle was both straightforward and brilliant. By placing an object, known as a gnomon, upright in the ground, ancient inventors created a stationary pointer. As the sun journeyed from east to west, the gnomon's shadow would sweep around it in a predictable arc, functioning as the hour hand on a giant, celestial clock face. The length and direction of this shadow provided a surprisingly accurate read on the time of day, turning an abstract concept into something visible, tangible, and measurable. The earliest iterations of this idea were monumental and communal. Think of the great obelisks of ancient Egypt, towering stone needles that served as much more than just impressive monuments. Their long, sharp shadows cast upon the ground became public timepieces for entire cities, dividing the daylight hours into segments for administrative duties, market openings, and religious ceremonies. These massive sundials were fixed in place, calibrated to the specific latitude of their location, and represented a shared understanding of time that governed daily life for thousands of people. They were the clock towers of the ancient world, anchoring a society's rhythm to the unwavering motion of the sun. But the story of the sundial didn't end with these enormous public installations. As civilizations like the Greeks and Romans refined the concept, they introduced a new level of precision and portability. Greek astronomers made a critical advancement by angling the gnomon to point towards the celestial pole, aligning it with the Earth's axis. This clever adjustment compensated for the changing altitude of the sun throughout the year, making sundials significantly more accurate across different seasons. The Romans, ever the practical engineers, then took this improved design and miniaturized it. They crafted intricate, portable sundials from bronze and even precious metals, some small enough to be carried in a pocket or worn as jewelry. For the first time, an individual could possess their own personal timepiece, a concept that feels remarkably modern. A wealthy Roman citizen might consult their portable sundial to avoid being late for a business meeting in the forum or a dinner party at a friend's villa, proving that the human concern with punctuality is far from a contemporary invention. These devices evolved into beautiful works of art, often engraved with intricate designs and calibrated for specific latitudes along the vast expanse of the Roman Empire. A traveler moving from Rome to Gaul would need a different sundial or at least adjustments to their existing one, highlighting an early challenge with non-standardized time. Despite their sophistication, sundials had an obvious and inherent limitation. They were utterly reliant on the sun. On cloudy days or at night, they fell silent and useless. This fundamental drawback would inspire the quest for a more reliable timekeeper, one that could function independently of the weather and continue its measure even after the sun had set. Yet for all their brilliance, sundials shared one fundamental flaw that ancient innovators were determined to solve: their total dependence on daylight. A cloudy afternoon or the depth of night brought all timekeeping to a halt, creating a pressing need for a clock that could function independently of the sun and stars. The ingenious solution to this problem emerged not from the sky, but from the most essential element of life itself, water. By harnessing this steady, predictable flow of liquid, civilizations across the globe gave birth to the clepsydra, or water clock, creating the world's first portable, all-weather timekeeping device. The basic principle was beautifully simple, yet it required remarkable precision to execute. A clepsydra typically consisted of two containers. The upper vessel was filled with water and featured a small, carefully calibrated hole at its base. Water would drip from this hole into the lower container at a constant rate. By marking lines on the inside of the lower vessel or watching a float rise with the water level, people could measure the passage of time. It was a continuous, quiet drip that carved out the hours, a mechanical river of time that flowed regardless of the weather or the time of day. This seemingly simple mechanism represented a monumental leap in human thought, the abstraction of time into a measurable, controllable flow, separate from the direct observation of the heavens. Different cultures refined the clepsydra for their own unique needs, and its applications were surprisingly diverse. In ancient Greece, the water clock became an essential instrument of democracy, particularly in the Athenian law courts. To ensure fair and equal representation for every side in a debate, speeches were strictly timed by a clepsydra. A specific amount of water would be allotted for each case, and when the vessel was empty, the speaker's time was up. This practice was so integral to justice that the phrase, "waiting for the water," became synonymous with a waiting one's turn to speak. It's a powerful reminder that the struggle to manage speaking time in meetings is a challenge literally thousands of years in the making. Meanwhile, in ancient Egypt, water clocks took on a more solemn and practical role, regulating the night watches of the palace guards. These clocks were often shaped like a long, narrow cone with a hole at the bottom. The interior was marked with 12 scales for the 12 hours of the night. As water slowly drained out over the course of the night, the decreasing water level would align with these scales, telling the guards exactly how much of their shift had passed and how much remained. This ensured vigilance and order through the darkest hours, proving that societal structure could now extend seamlessly from day into night. Perhaps the most sophisticated development of the water clock occurred in ancient China during the Song dynasty. Chinese engineers like Su Song elevated the clepsydra into a breathtaking marvel of hydraulic engineering and astronomical observation. His clock tower, built in the 11th century, was a massive mechanical masterpiece over 30 feet tall. It used a constant flow water wheel to drive an intricate chain drive mechanism, which in turn powered the rotation of an armillary sphere for mapping the stars and a celestial globe that accurately modeled the movement of planets. Most impressively, the clock featured automated figurines that would ring bells, beat drums, and clang gongs to announce the arrival of each new hour. This was no mere timekeeper. It was a monumental, automated cathedral to time itself, a physical manifestation of the universe's rhythm powered by nothing but the relentless, patient flow of water. While the water clock was a triumph of engineering, other ancient thinkers were tackling an even grander challenge, not just measuring the hours of a single day, but mapping out the entire year with precision. This brings us to one of history's most enduring and influential timekeeping creations, the Egyptian civil calendar. For the ancient Egyptians, predicting the annual cycle wasn't a matter of convenience. It was a matter of life and death, all centered around the behavior of their great river. The Nile was the source of all life in Egypt, and its annual flooding was the event around which all society revolved. This flood deposited rich, fertile silt across the farmland, creating the black land that sustained their civilization. But the inundation was unpredictable. If farmers planted too early, their seeds could be washed away. If they planted too late, the soil would be too hard and dry. The entire agricultural economy, and therefore survival itself, depended on knowing exactly when the floodwaters would arrive. Their search for a reliable signal led their astronomers to make a breathtaking celestial discovery. They noticed that just before dawn at a certain time each year, the brilliant star Sirius would reappear in the eastern sky after a period of being invisible, lost in the glare of the sun. This event, known as the heliacal rising, always occurred in mid-July and coincided almost perfectly with the beginning of the Nile's annual inundation. To the Egyptians, this was no mere coincidence. It was a divine connection. They named Sirius Sopdet, and they saw its reappearance as a celestial herald, a god sending a signal that the life-giving waters were on their way. This reliable, heavenly cue became the foundation for their new year and the cornerstone of their calendar. Using this astronomical anchor, Egyptian priest astronomers developed a brilliant and practical solution: a civil calendar of 365 days, divided into 12 months of 30 days each, with an additional 5 epagomenal days added at the end of the year. These extra days were considered to be outside the regular year, a time celebrated as the birthdays of the gods. This structure was a radical simplification. Unlike lunar calendars, which constantly fell out of sync with the solar year and required extra months to be added, this civil calendar marched forward at a steady, unchanging pace. It was a purely administrative tool, divorced from the messy complexities of moon phases, designed for scheduling taxes, organizing labor, and planning festivals. This calendar was a monumental achievement in abstraction. It was one of the first systems to treat a year as a fixed number of days, a concept we take for granted today. However, the Egyptians were acutely aware of its tiny imperfection. The true solar year is approximately 365¼ days long. Their calendar, by ignoring that extra quarter day, slowly drifted against the actual seasons at a rate of about 1 day every 4 years. This meant that over centuries, the official New Year's Day, marked by the rising of Sirius, would eventually occur in a different season altogether. A festival meant to celebrate the beginning of the flood might, after many generations, fall during the harvest. Yet rather than seeing this as a failure, the Egyptians embraced both systems. They continue to use their stable, predictable civil calendar for all daily administrative purposes, while priestly astronomers simultaneously maintained a separate, accurate lunar calendar for determining religious holidays, carefully adjusting it based on their constant observations of Sirius. They lived with 2 parallel timelines, one fixed and bureaucratic, the other fluid and celestial. This pragmatic approach gave them the best of both worlds: the simplicity of a standardized calendar for running a vast kingdom, and the accuracy of astronomical observation for maintaining their sacred connection to the cycles of nature. This 365-day framework was so effective and so elegant that it would later be adopted and modified by the Romans, forming the direct ancestor of the very calendar we use today, a lasting testament to the ingenuity born from the banks of the Nile. While the Egyptians were perfecting their calendar along the Nile, another powerhouse of ancient innovation was making its own profound contribution to how we slice up time, a contribution so fundamental we rarely even think about it. Travel northeast to the fertile lands between the Tigris and Euphrates rivers, the heartland of Mesopotamia, where the Babylonians were building an empire of knowledge. These weren't just warriors and rulers. They were brilliant mathematicians and astrologer priests with an obsession for the heavens. Their greatest gift to modern timekeeping wasn't a device, but a number system, a uniquely elegant way of counting that would echo through millennia and is the sole reason our hour is divided into 60 minutes and not 10 or 100. The Babylonians adored the number 60. Their entire numerical worldview was built on a sexagesimal system, meaning base 60. To us, using 10 as a base seems obvious. We have 10 fingers. But the Babylonians saw greater utility in 60. Why? Because 60 is what mathematicians call a superior highly composite number. In plain terms, it's incredibly easy to divide. It can be split evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made it fantastically practical for trade, construction, and especially for the complex fractions required in their astronomical calculations. Trying to divide a day or a circle into whole, equal parts with a base 10 system is messy, but with base 60, the possibilities are clean and numerous. This mathematical preference was deeply intertwined with their celestial observations. Babylonian astronomers meticulously charted the paths of the sun, moon, and planets. They believed the sky was a divine dome and a complete circle, which they naturally divided into 360 degrees, a number that is 6 times 60. This division of the circle was a direct application of their base 60 system. From there, the logic flowed beautifully. If the sun's journey across the sky traces a 360-degree arc each day, then pinning down smaller units of time meant subdividing that circle further. Their mathematical tools were perfectly suited for the task, making the leap to dividing the day into smaller portions a natural one. Their sophisticated astronomical work required precise time measurements that were far smaller than a full day. They needed to track the gradual movement of celestial bodies, and for that, they created their own units of time. They divided a full day and night into 12 equal parts called baru, or double hours. Each of these was then subdivided into 60 smaller units, which we can think of as their minutes, and those were further divided into 60 even smaller parts, their version of seconds. This elegant, nested 60s structure was the direct conceptual ancestor of our own system. This Babylonian framework didn't disappear with their empire. It was preserved and passed down through centuries of scholarly tradition. Greek astronomers, who greatly admired and built upon Babylonian knowledge, adopted this sexagesimal system for their own geometric and astronomical work. Later, medieval Islamic scholars and astronomers further refined these ideas, translating ancient texts and using sexagesimal divisions in their highly advanced celestial maps and timekeeping instruments. By the time the first mechanical clocks began to appear in European town squares in the 14th century, the scholars designing them were steeped in this long tradition. When they needed to create dials to display the time, they naturally turned to the established and mathematically superior system of base 60 division that had been used for over 2,000 years to measure the heavens. They divided the clock face into 12 hours, a nod to both the Babylonian double hours and simpler sundial conventions, and then each hour into 60 minutes and each minute into 60 seconds. We have been counting time the Babylonian way ever since, so the next time you glance at a clock, you're not just seeing the time, you're seeing the enduring legacy of ancient Mesopotamian mathematicians who looked at the sky and saw a perfect circle, best divided by 60. Across the plains of southern England stands perhaps the most iconic and enigmatic timekeeping device from the ancient world, Stonehenge. This sprawling ring of massive, weathered stones has captivated the human imagination for centuries, sparking endless debates about its purpose. While modern popular culture often paints it as a mystical site for druidic rituals or even an alien landing pad, one of the most compelling and evidence-backed theories reveals a far more practical, yet equally awe-inspiring, function. A growing body of archaeological and astronomical research suggests that Stonehenge was, in essence, a Neolithic astronomical computer, colossal stone calendar engineered to track the complex cycles of the sun and moon with stunning accuracy. To understand this, we must first step back and appreciate the sheer scale of the endeavor. The largest of these sarsen stones weigh up to 50 tons each. They were quarried from sites over 20 miles away, shaped with nothing but stone tools, transported across the landscape, and then precisely erected and capped with massive lintels. This was not a casual project. It was a multi-generational undertaking that would have required a highly organized society, sophisticated engineering knowledge, and a motivation powerful enough to justify such an immense investment of time and labor. For a farming community whose survival was tied directly to the seasons, that motivation was likely the desperate, vital need to predict the turning of the year. The most obvious and undeniable celestial alignment at Stonehenge is with the summer solstice. If you stand at the center of the stone circle and look through the entrance towards the heel stone, you are perfectly aligned to witness the sun rise directly over that marker on the longest day of the year. This event would have been a spectacular confirmation of the calendar's accuracy, a moment of triumph when the celestial prediction made by this stone machine came true. But the sophistication doesn't end with a single alignment. The entire arrangement seems to encode a much more complex understanding of the sky. The 56 Aubrey holes, pits encircling the monument, may have served as a primitive calculating system. By moving markers between these holes in a specific pattern, perhaps tracking the years, it's theorized that priests or astronomers could have predicted lunar eclipses. This is because 56 is a number that neatly correlates with the cycles of the moon, including the roughly 18-year Saros cycle, after which eclipses repeat. Furthermore, the architecture hints at a dual purpose, tracking both the solar and lunar cycles. While the main axis is solar, aligned with the solstices, several other stones and avenues appear to align with the extreme rising and setting points of the moon during its major standstill, an event that occurs only every 18.6 years. This integration of solar and lunar time suggests the builders of Stonehenge were not just simple sun worshippers. They were meticulous observers of the entire celestial dance, seeking to harmonize the two most powerful rhythmic forces in their sky. Viewing Stonehenge through this lens transforms it from a mysterious ruin into a testament to Neolithic genius. It was a permanent, immovable almanac carved from the earth itself. Its predictions would have dictated the most critical aspects of life: when to plant and when to harvest, when to gather for ceremonies to ensure the sun's return, and when to expect the awe-inspiring and potentially frightening spectacle of an eclipse. In a world without writing, this stone computer served as the community's communal memory and its oracle, a physical interface between the human world and the cosmic order. It allowed a society of farmers and herders to not just react to the seasons, but to anticipate them, to hold a measure of control over the chaos of nature, and to see their place within the vast, turning mechanism of the universe. Yet for all the grandeur of Stonehenge and the sophistication of the Babylonians, nothing could have prepared the world for the discovery that would shatter our understanding of ancient technology. In the early days of the 20th century, off the coast of the Greek island of Antikythera, sponge divers stumbled upon the wreck of a Roman cargo ship filled with marble statues and other treasures from the 1st century before the Common Era. Among these artifacts was an unassuming, heavily corroded lump of bronze and wood, which seemed so insignificant it was almost overlooked. It was only years later, as museum conservators began to carefully clean it, that the lump began to reveal its secret. It was not a statue or a piece of jewelry. It was a machine, a complex, gear-driven mechanism of such intricate design and precise engineering that its existence seemed to defy all historical logic. We now know it as the Antikythera Mechanism, and it stands as the most stunningly advanced timekeeping device to survive from the ancient world. This remarkable object, once housed in a wooden case about the size of a large shoebox, was effectively the world's first known analog computer. Its purpose was not merely to tell the hour of the day, but to model the entire known cosmos. By turning a hand crank on the side, a user could activate a complex series of at least 30 interlocking bronze gear wheels, which in turn drove a series of dials and pointers on the front and back of the device. These dials didn't just show the time. They displayed the positions of the sun and moon, the phases of the moon, and the locations of the 5 planets known to the ancient Greeks. It could predict solar and lunar eclipses with remarkable accuracy, and it even included a dial tracking the 4-year cycle of the Panhellenic Games, the ancient precursor to the Olympics. This was a portable, mechanical planetarium, a simulation of the universe's clockwork designed to be held in your hands. The engineering insight behind the mechanism is what makes it so breathtakingly modern. The ancient Greek designers understood a fundamental astronomical problem. The planets don't move at constant speeds across the sky. From our earthly perspective, they sometimes appear to slow down, stop, and even move backwards in a phenomenon called retrograde motion. To replicate this non-uniform motion mechanically, the creators of the Antikythera Mechanism employed a brilliant solution: a differential gear, a complex arrangement of gears that can add and subtract rotational speeds. This type of mechanism was not thought to have been invented until the 16th century, for use in modern automobiles. Its presence in a 2,000-year-old device is nothing short of revolutionary. proving that the Greeks had achieved a level of mechanical sophistication that would not be seen again for over a millennium. The existence of such a device forces us to completely reimagine the ancient world. The Antikythera Mechanism was not a one-off magical creation. It was a finely crafted, sophisticated instrument. Its inscriptions are detailed and meticulous, a user's manual etched in bronze. This implies it was not unique. It was likely a copy of a known design, perhaps even a luxury model produced for a wealthy, educated patron. Think of it as the high-end scientific calculator of its day. Its recovery from a shipwreck bound for Rome suggests this technology, or the knowledge behind it, was something to be traded and displayed, a testament to the owner's intellect and wealth. The most chilling thought is how much knowledge was lost. The Antikythera Mechanism is a single, salvaged page from a vast library of ancient technological manuals that were drowned by history. It is a ghost from a golden age of science that was almost completely erased, a whisper of a path not taken, where the mechanical age might have begun not in the 1700s, but in the time of Archimedes. While the Antikythera Mechanism represents a pinnacle of mechanical ingenuity, another ancient civilization halfway across the world was achieving a different kind of temporal mastery, one built not on gears but on mathematics and a profound cosmic vision. Far from the Mediterranean, in the lush rainforests of Mesoamerica, the Maya developed a calendar system of such staggering complexity and accuracy that it stands as one of the greatest intellectual achievements of the ancient world. Unlike a single device, the Maya system was a conceptual machine made of interlocking cycles of time, a grand philosophical framework that connected the rhythms of human life directly to the heartbeat of the universe itself. At the core of their system were not one, but three distinct calendars, each serving a unique purpose and operating in a mesmerizing syncopation with the others. The first, and perhaps most mysterious, is the 260-day cycle known as the Tzolk'in, or the Sacred Round. This wasn't tied to any obvious astronomical phenomenon like a solar year or a lunar month. Instead, it was a uniquely Maya invention, a spiritual and divinatory calendar that wove together 20-day names with 13 numbers. Imagine a system with two interlocking gears, one gear with 20 teeth, each representing a day with its own specific deity, omen, and energy names like a mixed crocodile, Ik wind, or Akbal night. The second gear has 13 teeth, representing the numbers 1 through 13. Every single day, both gears would click forward one position, creating a new combination of number and day name. It would take 260 distinct combinations, 13 times 20, for the two gears to return to their starting position and the cycle to begin anew. This 260-day cycle governed ritual life, determined the auspiciousness of days for everything from planting crops to waging war, and was used to name individuals and forecast their destinies based on the energy of their birth date. Operating simultaneously was the second calendar, the Hab. This was the Maya's practical, solar-based calendar for managing civil and agricultural life. Much closer to our modern calendar, the Hab consisted of 18 months, each with 20 days, followed by a short, 5-day period known as Wayeb. This brought the total to 365 days. These 5 days of Wayeb were considered extremely dangerous and unlucky, a time when the boundaries between the spiritual and physical worlds grew thin and chaotic forces could seep into the everyday. People would often stay home, avoid important activities, and engage in rituals to protect themselves during this precarious time. While the Hab was a close approximation of the solar year, the Maya astronomers were acutely aware that the true year is about a quarter of a day longer. Evidence suggests they understood the need for a leap year correction, a level of precision that many other ancient cultures struggled to achieve. The true genius of the Maya system, however, lies in how these two calendars interacted. The Tzolk'in and the Hab ran concurrently, like two independent spinning wheels. For any given day, there was a date from both calendars. This means a specific day would be identified by, for example, 4 Can in the Tzolk'in and 5 Pop in the Hab. The combination of these two dates would only repeat once every 52 years, which is the least common multiple of 260 and 365. This 52-year cycle, known as the calendar round, was a foundational period in Maya life. Its conclusion was a time of immense significance and trepidation. There was a fear that the gods might not allow the cycles to renew, that the sun might fail to rise and the world could end. To ensure cosmic continuity, they would perform elaborate new fire ceremonies, extinguishing all old fires in the realm and lighting a new, sacred flame to carry them into the next 52-year cycle. But the Maya gaze stretched far beyond the horizon of a single human lifetime. To track the vast, epic sweep of history and mythology, they developed a third system, the long count. This is arguably their most famous innovation, the one that sparked modern prophecies about the end of the world in 2012. The long count is a linear count of days from a fixed mythical starting point, a date the Maya believed corresponded to August 11th, 3114, before the Common Era in our Gregorian calendar. Rather than using cycles that constantly repeat, the long count simply accumulates days, allowing them to place any event, past or future, on a single, continuous timeline. They counted these days using a modified base 20 system. The basic unit was a day, or kn. 20 kns made a winnel, 18 winnels made a ton, a 360-day year, closer to the solar year than the 365-day hob. 20 tons made a katon, and 20 katons made a biakton, a period of over 144,000 days, or roughly 394 of our solar years. The much-discussed 2012 date was simply the completion of the 13th biakton since their creation date. They did not predict this as an apocalyptic end, but rather as a hugely significant milestone, a moment of profound cosmic renewal and the beginning of a new grand cycle, much like our own celebration of a new millennium. The long count allowed Maya scribes to inscribe dates on their monuments with pinpoint accuracy for thousands of years into the past and future, creating a historical record of unmatched scope in the ancient Americas. This system reveals a worldview where time was not a linear arrow marching blindly forward, but a sacred, layered substance. Each day carried the weight of its unique combination of Tzolk'in and Hob energies, while simultaneously occupying its specific, unchangeable point on the infinite highway of the long count. For the Maya, to know the time was to know your place in a vast, intricate, and divinely ordered cosmic mechanism. High in the Andes Mountains, the Inca Empire forged a civilization entirely in tune with the cosmos, and at the very heart of their celestial worship stood a testament to their architectural and astronomical genius, the Coricancha, or Golden Enclosure, in their capital city of Cusco. This temple was not merely a place of worship, it was the spiritual and geographical axis of the entire Inca universe, a physical declaration of their intimate bond with the sun god, Inti. The Incas believed their emperor, the Sapa Inca, was a direct descendant of Inti, making the sun's life-giving power the literal foundation of their political authority and their very existence. Every aspect of the Coricancha was designed to reflect this divine connection, and its construction was a masterpiece of both devotion and precision engineering, with stones cut and fitted together so perfectly that not even a blade of grass could slide between them, all without a single drop of mortar. The temple's interior was a breathtaking display of wealth and reverence, famously sheathed in solid gold. Golden llamas grazed in golden gardens, and intricate gold plates lined the walls, all designed to capture and magnify the first and last rays of the sun each day, filling the sacred space with a dazzling, otherworldly light. But the most significant object was the punchao, a massive, oval-shaped disc of pure gold that represented Inti himself. This was far more than a static idol. Many scholars believe it functioned as a highly sophisticated solar marker. Positioned with intentional precision, it's thought that sunlight entering through specific trapezoidal windows would strike the disk's surface at key moments, such as the solstices and equinoxes, creating brilliant points of light or defined shadows that would crawl across its surface to mark these pivotal celestial events. In this way, the disk acted as the heart of a giant temple-sized sundial, its gleam serving as a direct, visible communication from the god it represented. The architecture itself was the mechanism. The Coricantia's walls and courtyards were punctuated by carefully aligned portals and strategically placed stone pillars, called sukankas, on the horizon. These features worked in concert to create a precise calendar etched in light and shadow. During the June solstice, the sun would rise in perfect alignment with one specific window, flooding a designated area of the temple with a concentrated beam of light, likely illuminating a sacred stone or a particular section of the gold-lined wall. Conversely, during the December solstice, the sun would set in alignment with another portal, casting long, specific shadows that would signal the turning of the season. These events were not hidden knowledge. They were public, dramatic affirmations of the Sapa Inca's power and the priesthood's wisdom, reinforcing the social order by demonstrating a tangible command over the cycles of nature. This celestial observation was inextricably linked to the Incas' most practical need, agriculture. The precise timing of the solstices told them exactly when to plant and when to harvest their crops at various altitudes in the challenging Andean environment. A festival called Inti Raymi, the Festival of the Sun, marked the June solstice, a time of offering and celebration to beseech Inti to return from his farthest point and ensure the life-giving warmth would come back to the land. The Coricantia was the central node in a vast network of sacred sightlines, or sects, that radiated out from Cusco across the empire, connecting hundreds of shrines and markers on the landscape. This meant the entire empire was literally oriented around the cosmic principles embodied by the temple, making Cusco not just a political capital, but the true navel of the world. The Spanish conquistadors, upon seeing the Coricantia, were astounded by its wealth and systematically looted its gold, melting down the sublime Punchao and building the Church of Santo Domingo directly upon its sacred foundations. Yet even today, the incredibly sturdy stonework of the Inca temple endures, visible beneath and around the colonial structure, a silent, enduring stone skeleton that still whispers of a time when an empire told time by watching sunlight dance across gold. While the Incas were building their empire in alignment with the sun, on the other side of the world, Chinese astronomers were engaged in an even more ambitious project, mapping the entire heavens with systematic precision. For millennia, the imperial courts of China supported dedicated bureaus of astronomers whose task was to observe, record, and interpret every celestial event. This was about more than crafting a calendar. It was a fundamental duty of the state, directly tied to the emperor's mandate of heaven. The Chinese believed that the cosmos and the earthly realm were intimately connected, that harmony in the heavens reflected a virtuous ruler, while strange celestial occurrences, comets, nova, sunspots, could be dire warnings of misrule or impending disaster. It was the astronomers' sacred task to read these signs and advise the emperor accordingly, making their work a critical pillar of governance and stability. This profound responsibility led to the creation of the world's most meticulous and long-running astronomical records. Court astronomers kept daily logs of the skies for over 2,000 years, creating an unparalleled archive of observations. They documented every unusual event with painstaking detail. A record from 1,352 years before the Common Era describes a guest star, now known to be the supernova that created the Crab Nebula, visible even in daylight for 23 days. These chronicles are so precise that modern astronomers still use them to study the long-term behavior of stars and other cosmic phenomena. This relentless dedication to data collection allowed them to identify patterns and cycles with incredible accuracy, leading to the development of calendars that were refined continuously over centuries. Their calculations for the solar year and the lunar month became so precise that their calendar could predict eclipses and solstices with remarkable reliability, further reinforcing the emperor's role as the son of heaven and the mediator between the cosmic and human realms. The tools they developed to make these observations were equally sophisticated. The crown jewel of Chinese astronomical instrumentation was the armillary sphere. This was not a simple model. It was a complex, ringed instrument designed to represent the celestial sphere itself. A series of concentric bronze rings, each meticulously calibrated, depicted key circles like the celestial equator, the ecliptic path of the sun, and the horizon. The entire apparatus could be rotated to simulate the apparent daily motion of the stars around the Earth. By sighting a star or planet through the central sighting tube and reading its position against these graduated rings, an astronomer could pinpoint its location in the sky with mathematical precision, tracking its movements over time. This allowed them to create detailed star charts and catalogs far more advanced than anything in the contemporary West. The development of the armillary sphere is a story of constant innovation. The first basic models appeared during the Han Dynasty, but it was during the Song Dynasty that the brilliant scientist and statesman Su Song, whom we met with his water clock, integrated a powered armillary sphere into his colossal clock tower. His design used a water-driven escapement mechanism to rotate the sphere automatically, keeping perfect pace with the actual rotation of the heavens. This created a real-time, mechanical model of the universe, a working simulation that could be used for both calculation and demonstration. Later, during the Yuan Dynasty, the legendary astronomer Guo Shaojing refined the design even further, stripping it down to its essential components to reduce error and increase accuracy. His simplified armillary sphere could make measurements with a precision that would not be matched in Europe for centuries. These tools and records culminated in breathtakingly detailed star maps. One of the most famous, the Dunhuang star chart, dating from the Tang Dynasty, is the oldest complete preserved star atlas in the world. Painted on paper, it depicts over 1,300 stars grouped into 257 distinct constellations, all positioned with astonishing accuracy. But the Chinese approach to constellations was vastly different from the Greco-Roman tradition that influenced the West. They weren't connecting stars to create pictures of mythological heroes. They were building a celestial bureaucracy. The sky was a mirror of the imperial court, filled with palaces, ministries, markets, and armies of stars. The North Star was the supreme palace, the unchanging seat of the celestial emperor, around which all other stars, his loyal courtiers, dutifully revolved. This wasn't just whimsical storytelling. It was a complete cosmological framework that justified the social and political order on Earth, making the precise measurement of the heavens absolutely essential for maintaining harmony in the empire. If you think your calendar is confusing with its occasional leap years and shifting holidays, you would have been utterly lost in early Rome. Their first attempts at timekeeping were, to put it mildly, a spectacular mess. Legend attributes the original Roman calendar to the city's mythical founder, Romulus, and it was a crude, 10-month lunar system that began in March and ended abruptly in December, leaving a nameless, unaccounted for gap of about 60 days in the dead of winter. This calendar was primarily a tool for priests, and its short 304-day year drifted against the seasons so rapidly that it became useless for agriculture within just a few years. The situation was so dysfunctional that an early king, Numa Pompilius, is said to have attempted a fix around 700 B.C.E. by adding 2 new months, January and February, to the end of the year, creating a 12-month cycle. He also tried to align it closer with the lunar year by creating a system of 12 lunar months totaling 355 days. But this was still about 10¼ days shorter than the actual solar year. To prevent the calendar from completely spinning out of control, the Romans inserted an extra month, called intercalaris or Mercedonius, every couple of years. This wasn't a standardized leap month added on a fixed schedule. Its insertion was entirely at the discretion of the pontifices, the high priests who oversaw the calendar. This power soon became a tool for political manipulation. A priest friendly to a particular politician could lengthen a year in which that politician held office, giving them more time to enact their agenda. Conversely, they could shorten the term of a political enemy. By the time of Julius Caesar, this manipulation had become so rampant that the civic calendar was out of sync with the solar year by a staggering 3 months. The spring festival meant to celebrate planting was occurring in the dead of winter. and the harvest holidays were taking place before the seeds had even been sown. Roman time was, quite literally, broken. Enter Julius Caesar. Fresh from his campaigns in Egypt, he was surrounded by advisors who had witnessed the superior efficiency of the Egyptian solar calendar, the very same 365-day system we discussed earlier. Caesar recognized that a reliable calendar was essential for administering a vast, sprawling empire. He couldn't collect taxes, schedule military campaigns, or hold festivals if no one could agree on what day or season it actually was. In 46 B.C.E., with the help of the brilliant Alexandrian astronomer Sosigenes, Caesar embarked on the most radical calendar reform the world had ever seen. To correct the massive drift that had accumulated, he first had to reset the clock. He declared that the year 46 B.C.E. would last for 445 days, a period Romans wryly called the last year of confusion. This monumental year was necessary to drag the Roman calendar back into alignment with the seasons. Then, for the new year 45 B.C.E., he launched the Julian calendar. This new system abandoned the unreliable lunar cycle almost entirely in favor of a purely solar year. Sosigenes had calculated the solar year to be 365.25 days long. Caesar's brilliant solution was to institute a common year of 365 days, and to account for that leftover quarter day, he decreed that an extra day would be added to every fourth year. This was the birth of the leap year. The calendar itself was also rationalized. He standardized the lengths of the months, giving us the familiar 30 and 31-day alternations we know today, with the exception of February. He also moved the new year from March to January, a month named for Janus, the two-faced god of beginnings and endings, who looks both backward and forward, a perfect symbol for the turn of the year. This new system was a masterpiece of bureaucratic efficiency. It was stable, predictable, and, for its time, incredibly accurate. The Julian calendar was Caesar's enduring legacy, outlasting his own life and becoming the foundational timekeeping structure for the entire Western world for over 16 centuries. It was the calendar of the Roman Empire, the medieval kingdoms, and the early Renaissance. It enabled scientists to make long-term observations, governments to plan for the future, and societies to function with a shared understanding of time. Of course, Sosigenes' calculation was off by just 11 minutes and 14 seconds per year. That tiny error meant the calendar still drifted, losing about one day every 128 years. This slow creep would eventually lead to another reform centuries later with the Gregorian calendar, but that is a story for another time. The crucial point is that Caesar's reform transformed time from a chaotic, politically manipulated concept into a stable, measurable framework. He gave the Western world the gift of order, a system so effective that its basic structure, the leap year, remains the beating heart of our modern calendar today. While the Romans were standardizing time across their empire with a reformed calendar, a very different kind of precision was being mastered far to the north, not with ink and parchment, but with crystal and sunlight. The Vikings, those legendary seafarers from Scandinavia, undertook voyages of staggering audacity, crossing the treacherous, fog-shrouded North Atlantic to reach Iceland, Greenland, and even the shores of North America centuries before Columbus. Their success is one of history's great navigational puzzles. Without a magnetic compass, and often sailing under skies where neither the sun nor stars were visible for days on end, how did they possibly find their way? The answer may lie in a mysterious object mentioned in the sagas, the Solar Stein, or Sunstone. The Viking sagas, those epic tales of exploration and adventure, make fleeting but fascinating references to this special stone. In one story, the weather is so grim and overcast that the king becomes concerned about losing his way. He is handed a sunstone, holds it up to the sky, and is instantly able to pinpoint the sun's location, saving the day. For centuries, historians dismissed this as mere legend, a piece of magical folklore. But in the late 1960s, a Danish archaeologist named Thorkild Ramsku proposed a brilliant and scientifically grounded theory. He suggested the sunstone was not a myth, but a real, transparent crystal capable of a remarkable trick, detecting the polarization of sunlight. To understand how this works, imagine a completely overcast day. The sun itself is completely hidden, a diffuse, gray glow illuminating the sky from everywhere and nowhere at once. To our eyes, it offers no directional information. But sunlight, even when scattered by clouds and mist, is polarized, meaning its light waves vibrate in a specific orientation. A crystal like Iceland spar, a form of calcite found in Scandinavia, has a unique property called birefringence. When you look through it, you see a double image, but crucially, the brightness of these two images changes as you rotate the crystal. By turning the stone until the two images appear equally bright, a navigator could determine the exact angle of the polarized light in the sky, and from that, deduce the hidden sun's position with an accuracy of within a single degree, even hours after sunset. This wouldn't have been their only tool, of course. Viking navigation was a multi-layered art. They were masters of dead reckoning, using a sandglass to measure time and a log to estimate speed, calculating the distance traveled. They watched for signs in nature, the flight paths of birds returning to land, the specific types of seaweed floating in the water, and the direction of ocean swells, which can persist long after the wind that created them has died down. They possessed a detailed mental map of the coastlines and a deep oral tradition of sailing directions. The sunstone, therefore, wasn't a magical GPS device. It was the crucial component that could calibrate their entire system on those critical days when their primary celestial guides vanished. On a long voyage, being off by just a few degrees could mean missing an island entirely and sailing on into the empty ocean. So this kind of precision was the difference between life and death. The theory moved from intriguing speculation toward probable fact with a groundbreaking scientific study published in 2011. Researchers took a piece of Iceland spar and tested its efficacy under a range of cloudy and twilight conditions. The results were startling. Using the crystal, they could locate the sun's position with an accuracy that rivaled modern instruments. Then, in 2013, a team of archaeologists made a tantalizing physical discovery. During the excavation of an English shipwreck from the 1592, the Alderney wreck, they found a rectangular block of Iceland spar, carefully cut and polished, nestled near a pair of navigational dividers and other tools. While this ship was Elizabethan and not Viking, it provides the first tangible proof that such crystals were indeed carried aboard ships and were almost certainly part of a navigator's toolkit, validating a practice that the Vikings likely pioneered centuries earlier. This combination of saga, science, and archaeology paints a picture of the Viking navigator not as a brute relying on luck, but as a sophisticated technician, reading the subtle language of light itself. Holding his sunstone up to a featureless gray sky, he would slowly rotate it, his eyes searching for the moment the twin images achieved perfect balance. In that moment of clarity, he would know. He would turn and point toward a horizon that looked no different from any other, and confidently give the heading, his faith placed not in magic, but in a profound understanding of the natural world's hidden geometry. This crystal was their secret weapon against the elements, a testament to their ingenious adaptation that allowed them to conquer the most formidable seas on Earth. While the Vikings mastered the art of navigation across physical oceans, ancient Indian scholars were embarking on a profound journey across the ocean of time itself, developing systems of such philosophical depth and mathematical precision that they redefined the very scale on which time could be measured. At the heart of their practical timekeeping was a foundational text known as the Vedanga Jyotisha, one of the 6 auxiliary disciplines essential for understanding and correctly performing the Vedic rituals. This text, composed sometime between 1400 and 800 years before the Common Era, is far more than a simple calendar. It is a manual that intricately weaves astronomy, mathematics, and liturgy into a single, sacred science. Its opening verse makes its purpose gloriously clear. Like the crest of a peacock, like the gem on the head of a snake, so is Jyotisha Shastra standing at the head of all Vedangas. Timekeeping was placed at the very pinnacle of sacred knowledge because without it, the entire spiritual edifice of Vedic life would collapse. The primary goal of the Vedanga Jyotisha was desperately practical for its time, to ensure that the elaborate and powerful Vedic sacrifices, or yajnas, were performed at the exact, astronomically auspicious moment to maximize their efficacy. A ritual intended for the spring equinox performed even a day late would be, in their view, spiritually useless. To prevent this, the text provides detailed rules for tracking the movements of the sun and the moon against the backdrop of the 27 or 28 nakshatras, the lunar mansions that formed the zodiac of ancient India. It meticulously calculates the length of the solar year, the lunar month, and the cycles of intercalation, the adding of extra months required to keep the lunar and solar calendars in harmony, a system known as the luni-solar calendar. Their calculated year was 366 days, a remarkably close approximation that allowed priests to predict the seasons and plan the ritual calendar years in advance. This was timekeeping in service of cosmic order, or Rita, a way of aligning human activity with the unwavering rhythm of the universe to maintain balance and harmony. Yet for all its practical brilliance, the Vedanga Jyotisha was merely the gateway to a far more expansive and mind-bending conception of time. If this text dealt with the time of humans and rituals, the concept of the yugas dealt with the time of the gods and the cosmos itself. Hindu cosmology presents time not as a linear arrow, but as a cyclical spiral, with the universe going through endless repeats of creation, preservation, and dissolution. The basic unit of this cosmic cycle is the yuga, a staggering epoch of thousands of divine years. 4 yugas make up one full cycle, or Mahayuga, each one representing a progressive decline in spiritual wisdom and human virtue, much like the Greco-Roman ages of gold, silver, bronze, and iron. The numbers involved are almost incomprehensible to the human mind. The first and most perfect age, the Satya Yuga, lasts for 1,728,000 human years. This is followed by the Treta Yuga for 1,296,000 years, the Dvapara Yuga for 864,000 years, and finally, the Kali Yuga, the age of darkness and conflict we are currently believed to be in, which lasts for 432,000 years. These 4 ages together total 4,320,000 years to form a single Mahayuga, but the scale expands even further. 1,000 of these Mahayugas form a single day of Brahma, the creator god, known as a kalpa, a period of 4.32 billion years. Brahma's night is of equal length, and his entire lifespan is 100 of these divine years, after which the entire universe dissolves back into its unmanifest state until the next Brahma is born. This makes the total lifespan of a universe 311,040 billion years, a number so vast it makes the entire history of our own science and civilization seem like the briefest flicker of a candle in the cosmic dark. This was not meant to be a literal, scientific chronology, but a profound philosophical framework designed to instill a specific worldview. The Yuga system presents a universe of unimaginable vastness, emphasizing the transient, fleeting nature of all human concerns against the backdrop of eternity. It teaches that decline and renewal are inherent to existence, that dark ages like the Kali Yuga are not permanent endings, but merely one phase in an endless, repeating cycle. This cosmological perspective encouraged detachment from temporary material struggles and a focus on eternal spiritual truths. It is a humbling and awe-inspiring vision, one that challenges our modern, linear perception of history and progress, suggesting that time is not a river flowing in one direction but a great wheel, turning slowly through ages of light and darkness, with each revolution containing the potential for liberation. While the Indian Yuga system contemplated the cosmic scale of eternity, another civilization was achieving a different kind of mastery over time, one focused on breathtaking accuracy within the human scale of the solar year. Far to the west, in the heart of the Persian Empire, a group of the medieval world's greatest minds gathered under the patronage of Sultan Jalal al-Din Malik Shah to solve a problem that had plagued timekeeping for centuries: the slow, inexorable drift of the calendar against the seasons. Their creation, the Jalali calendar, would stand for centuries as the most accurate solar calendar ever devised. The catalyst for this reform was the same fundamental flaw that had necessitated Julius Caesar's intervention: the tiny, accumulating error inherent in any calendar system. The Persian Empire was using a Zoroastrian calendar that, much like the early Roman system, had slowly fallen out of sync with the astronomical reality. This misalignment caused significant confusion for administering a vast empire, disrupting tax collection, agricultural planning, and the timing of religious festivals. Sultan Malik Shah, a Seljuk ruler known for his support of the sciences, commissioned an extraordinary team of astronomers, including the legendary poet and mathematician Omar Khayyam, to correct the calendar once and for all. Their observatory in Isfahan became the nerve center for this ambitious project, where they made meticulous observations to measure the length of the tropical solar year with unprecedented precision. The system they developed, officially implemented in 1079 of the Common Era, was a marvel of mathematical elegance. At its core was a revolutionary leap year system far more sophisticated than the simple, every 4 years rule of the Julian calendar. Omar Khayyam and his colleagues calculated the solar year to be 365 and a fraction days, and that fraction was an exquisitely complex 365.24219858156 days. To accommodate this, they abandoned the concept of adding a full day at fixed intervals. Instead, they devised a 33-year cycle of leap years that distributed the extra time with remarkable subtlety. The rule was elegant. Within each 33-year period, there would be 8 leap years, but these weren't spaced evenly every 4 years. The cycle was arranged so that the leap years would typically occur every 4 years, but after a sequence of these, there would be a single 5-year gap without a leap day. This pattern of 7 cycles of 4 years and 1 cycle of 5 years within the 33-year master cycle allowed them to almost perfectly mirror the actual movement of the Earth around the Sun. The impact of this precision was immediate and profound. The Persian New Year, Nowruz, which marks the vernal equinox and the beginning of spring, was now permanently fixed to its rightful astronomical moment. For an agricultural society, this was a monumental achievement. Farmers could rely on the calendar to tell them the exact optimal time for planting and harvesting, year after year, generation after generation, without any drift. The Jalali calendar became the bedrock of Persian civil life, governing everything from fiscal cycles to cultural celebrations with a reliability that the Western world would not achieve for another 500 years. This calendar was more than an administrative tool. It was a powerful symbol of a golden age of Islamic science, a period when the Muslim world was the undisputed global center of astronomy, mathematics, and intellectual inquiry. The Jalali calendar's legacy endures vibrantly today. It is the official calendar of Iran and Afghanistan, a living testament to the genius of its 11th century creators. Every time Nowruz is celebrated precisely at the moment the sun crosses the celestial equator, it is a silent, global homage to a team of astronomers who look to the heavens and, with pen and parchment, manage to capture the sun's journey in a net of perfect numbers. This unyielding need for temporal order found its ultimate expression in the divine office, the rigorous schedule of daily prayers that structured monastic life. This wasn't a mere suggestion of devotion. It was the very heartbeat of the monastery, a sacred cycle known as the canonical hours that divided both day and night into segments for worship. The day began in the deep darkness before dawn with matins, the longest and most solemn service, followed by lauds at first light. Throughout the day, prayers marked the major divisions: prime at the first hour, terce at the third, sext at the sixth, and none at the ninth. As dusk fell, vespers offered evening praise, and compline provided a final prayer before sleep. This unceasing rhythm of prayer was believed to sanctify time itself, with the monks' voices rising in a continuous chant of praise that echoed the perpetual worship of the angels in heaven. To fail in this duty was to break a sacred chain, making the accurate measurement of time a spiritual imperative, not just a practical one. Within the secluded stone walls of the monastery, the celestial clock of the sun and stars was often invisible, and the chaotic, seasonal time of the peasant farmer outside was utterly irrelevant. The monastic community needed to create its own autonomous, perfectly regimented timeline. This led to the preservation and sophisticated refinement of ancient timekeeping technologies that had fallen into disuse elsewhere in Europe. The water clock, or clepsydra, found a new home in the scriptorium in cloister. Monastic artisans became experts in building and maintaining these devices, crafting intricate systems where the steady drip of water from one vessel to another would eventually trigger a mechanism, perhaps a small bell, a weight that dropped, or even a simple flag that became visible to signal to the horologist monk that it was time to ring the bells for the next office. These were not the monumental public clepsydry of antiquity, but practical, functional engines of devotion, their constant, gentle trickle, a liquid metronome for a life of prayer. Alongside water, they also mastered the use of fire to mark the passage of time. The candle clock was a beautifully simple yet effective solution. Craftsmen would produce candles of a highly consistent wax composition and thickness, often marked at regular intervals. As the candle burned steadily down past each mark, it indicated that a specific period, perhaps an hour, had elapsed. In some larger institutions, elaborate metal contraptions were even built around the candle. As it burned down, it would release a small weight that would clatter onto a metal plate, creating an audible alarm to rouse the monk on duty from his contemplations or his sleep for the night offices. This marriage of simple technology and sacred duty ensured that the rhythm of prayer never faltered, turning the monastery into a kind of temporal fortress, insulated from the unpredictable flow of the natural world outside its gates. The monk assigned as the horologist held a position of grave responsibility. His vigilance ensured the spiritual integrity of the entire community. While others slept, he would watch the water flow or the candle burn, his own prayer cycle intertwined with his duty to mark the time for others. His call would send a younger novice scurrying up the winding stairs to the bell tower to pull the ropes, sending the peals echoing across the monastery grounds and out into the surrounding countryside. For the local population, the monastic bells became the first public time signal, a shared marker of the day's progression that was more reliable than the position of the sun. This regimented and measured time was a radical departure from the fluid, task-oriented time of medieval peasant life, representing a crucial step in the journey toward the modern conception of time as a universal, abstract commodity that could be divided, managed, and saved. Yet even with the regulated drips of water clocks and the steady burn of candles, the medieval world craved a timekeeper that was more portable, more reliable, and utterly immune to the elements. The answer arrived not with a complex mechanism, but with a simple yet perfect reversal of an ancient principle. For millennia, humanity had measured time by watching something empty, the shadow sweep across a dial, the water drain from a vessel. But a new invention flipped this concept, creating a device that measured time by watching something accumulate. This was the hourglass, a deceptively simple instrument whose quiet revolution was powered by nothing more than the relentless flow of sand. Its genius lay in its elegant consistency. Two glass bulbs connected by a narrow neck held a precise quantity of fine, dry sand. When inverted, gravity took over, pulling each grain through the calibrated opening at a constant, predictable rate. The entire contents would funnel from the top bulb to the bottom in a fixed period, an hour, 30 minutes, or even just a few moments. Unlike water, the sand wasn't affected by freezing temperatures or evaporation. Unlike a candle's flame, it wasn't vulnerable to a stray draft. It offered a self-contained, repeatable, and perfectly reliable measure of duration that could be used anywhere, anytime, simply by turning it over. The hourglass didn't tell you what time of day it was. It told you how much time had passed, a crucial distinction that made it the perfect tool for managing tasks and routines. Nowhere was this reliability more critical than aboard a ship at sea. Before the age of precise marine chronometers, Navigating the open ocean was a terrifying exercise in dead reckoning. A captain could plot a course, but judging the ship's speed was guesswork. The hourglass provided the solution, becoming the beating heart of the vessel's daily operation. The ship's boy, often the youngest member of the crew, was given the solemn duty of tending the half-hour glass. His entire existence was governed by its flow. As the last grain of sand fell, he would ring the ship's bell and immediately flip the glass to begin the next cycle. This system divided the day into watches, with a specific number of bell strikes marking the passage of each half-hour segment. This regimented structure organized the crew's lives, dictating their shifts for sailing, sleeping, and eating, and ensuring someone was always alert at the helm. It was also essential for navigation. By using a log line thrown overboard to measure the ship's speed through the water and timing its travel with a half-hour glass, the navigator could estimate the distance traveled, a vital piece of data for plotting their position on a vast, featureless sea. On solid ground, the hourglass found a different but equally vital purpose, governing the spoken word. In churches across Europe, it became known as the pulpit hourglass. Placed prominently on the lectern, its silent stream served as a gentle but firm moderator for the preacher's sermon. A typical glass might be set for an hour, and its presence ensured that the congregation's spiritual edification didn't tip over into sheer endurance. It protected listeners from overly enthusiastic orators and encouraged preachers to structure their messages with clarity and conciseness. This practice was so widespread that the image of an hourglass became synonymous with mortality and the finite nature of life, a memento mori reminding all present that their time on earth, like the sand in the bulb, was steadily running out. Its utility spread rapidly into other facets of daily life. Universities employed them to ensure professors did not overrun their lectures, and law courts used them to allot equal time to opposing sides in a debate, much like the clepsydry of ancient Athens. In the home, smaller versions, sometimes called egg glasses, were used in the kitchen to time the boiling of an egg or the proofing of bread, bringing precise measurement into domestic routines. The hourglass democratized time, moving it out of the monastery and the university and into the hands of sailors, cooks, and tradesmen. It was a personal, affordable, and utterly dependable machine that made the abstract concept of a duration something tangible, visible, and manageable for everyday life. Its silent trickle becoming one of the most familiar sounds of progress in the medieval world. Across the vast and varied landscapes of North America, long before European contact, indigenous peoples were developing their own sophisticated and deeply spiritual relationships with the cycles of time, etching their understanding of the cosmos into the very earth itself. Unlike the monolithic structures of Europe or the written records of Asia, much of this knowledge was conveyed through oral tradition and landscape architecture, leaving behind enigmatic archaeological sites that we are still striving to fully comprehend. These structures, from massive earthen mounds to precise stone circles, were not crude attempts at imitation. They were unique, brilliant innovations born from a profound connection to the land and sky, serving as both calendar and cathedral for their creators. In the fertile Mississippi River Valley, near present-day St. Louis, the city of Cahokia stood as one of the largest urban centers in the pre-Columbian world, a bustling metropolis that was home to tens of thousands of people. At its heart lay a grand public plaza, dominated by a series of immense earthen mounds. The most famous of these, Monk's Mound, is a colossal terraced pyramid that covers more than 14 acres and rises 100 feet into the air. But the true genius of Cahokia's timekeeping is found not just in the mounds themselves, but in their precise arrangement. Archaeoastronomers have discovered that the entire central plaza is a carefully designed celestial observatory. A large circular feature west of Monk's Mound, now known as Woodhenge, was reconstructed based on post-hole patterns found in the soil. This circle of massive cedar posts acted as a horizon calendar. By standing at a designated post in the center on the morning of the equinox or solstice, a priest or astronomer would see the sun rise directly over another specific post on the perimeter, signaling the change of season to the entire community. This knowledge was essential for coordinating the agricultural cycle that fed Cahokia's immense population, marking the precise times for planting corn, beans, and squash. Far to the west, high in the alpine meadows of the Bighorn Mountains in Wyoming, another stone structure whispers of ancient celestial wisdom. The Bighorn Medicine Wheel, a spoked wheel of stones nearly 80 feet across, sits at an elevation of nearly 10,000 feet, its remote location offering an unobstructed, panoramic view of the horizon. Each of the cairns at the end of its 28 spokes aligns with a specific astronomical event. The most prominent alignments point to the summer solstice, sunrise, and sunset, while other cairns frame the rising points of bright stars like Sirius, Aldebaran, and Rigel, which were crucial for marking specific times of the year before the sun's journey provided a clear signal. The number 28 is highly significant, echoing the number of days in a lunar month. This has led many researchers to suggest the wheel was a complex lunisolar calendar, a device that could reconcile the cycles of the moon with the longer solar year. For the Plains tribes, who followed the great migratory herds of bison, such a calendar was not about agriculture but about movement and ceremony. Knowing precisely when the solstice would occur or when a certain star would first appear in the dawn sky could dictate the timing of a sacred hunt, a major gathering, or a pivotal seasonal migration. Beyond these grand architectural feats, evidence of timekeeping is also found on a more intimate scale, carved into rock faces across the continent. Petroglyphs, images pecked into stone, and pictographs, paintings made with mineral pigments, often contain celestial symbolism that modern researchers are only beginning to decode. At places like Chaco Canyon in New Mexico or the Columbia River Gorge in the Pacific Northwest, spiral symbols are frequently associated with light shading phenomena. At specific times, like the summer solstice, a dagger of sunlight will pierce a rock formation and move across one of these spirals, its beam illuminating the center of the coil at the exact moment the sun reaches its highest point in the sky. These light interactions served as a confirmatory event, a dramatic, public validation of the priest's predictions and the cosmic order. Other petroglyph panels are covered in precise dot patterns and intricate arrays of lines. Some anthropologists theorize these could represent star maps or tally counts for recording lunar cycles, perhaps even tracking the more complex 18.6-year cycle of the moon's orbital precession, much like the Aubrey holes at Stonehenge. A shaman or timekeeper might have used these permanent stone calendars to teach apprentices, to keep a long-term record of eclipses, or to plan for ceremonies that required absolute celestial precision. The knowledge encoded in these stones was sacred, a form of science intertwined with spirituality that ensured the community remained in harmony with the powerful, unseen forces governing the universe. These sites collectively reveal a continent rich with astronomical ingenuity, where time was not taken from a clock but received from the sky, a continuous gift that dictated the rhythm of life, ceremony, and survival for thousands of years. While the hourglass brought reliable timekeeping to the decks of ships and the halls of justice, a parallel revolution in precision was unfolding in the vibrant intellectual centers of the Islamic world. During what is often called the Golden Age of Islam, stretching from the 8th to the 14th centuries, a culture of learning and innovation flourished from Baghdad and Damascus to Cordoba and Cairo. Caliphs and sultans actively sponsored the translation of knowledge from Greek, Persian, and Indian sources, creating vast libraries and attracting the greatest scholarly minds of the era. It was within this rich environment that timekeeping was elevated from a practical art to a sophisticated science, culminating in the creation of instruments of breathtaking elegance and utility, most notably the astrolabe. Often described as the smartphone of the medieval world, the astrolabe was a compact, multi-functional computer made of finely crafted brass. In the hands of a skilled user, this device could solve a staggering array of problems related to time, astronomy, and navigation. Its design was a masterpiece of mathematical projection, a two-dimensional representation of the three-dimensional celestial sphere. The core of the instrument was a disc-like mater, or mother, which held a series of interchangeable engraved plates, each calibrated for a specific latitude. On top of these sat a pierced disc called the Rete, a complex star map with pointers marking the positions of the brightest stars, which rotated over the plates to simulate the daily motion of the heavens. By holding the astrolabe by its ring, allowing it to hang vertically, and then sighting the sun or a specific star through the alidade, a movable sighting bar on the back, a user could measure its altitude above the horizon. This single measurement unlocked a world of information. By rotating the Rete to match the observed altitude, the entire sky for that moment was laid out on the dial. The most immediate and vital function for daily life was telling the time, both during the day and at night. But for an Islamic society, its utility went far deeper. One of the 5 pillars of Islam is prayer or salat, which must be performed at 5 specific times each day. These times are not fixed to a clock but are defined by the sun's position: Fajr at dawn, Dhuhr when the sun passes its highest point, Asr in the afternoon when an object's shadow equals its length, Maghrib at sunset, and Isha at nightfall. The astrolabe could calculate these prayer times with remarkable accuracy for any day of the year and any location, making it an indispensable tool for religious observance and unifying communities across the vast Islamic empire in their daily rituals. Beyond its role as a timepiece and prayer aid, the astrolabe served as a sacred compass. Another pillar of Islam is the Hajj, the pilgrimage to the holy city of Mecca, which every able-bodied Muslim must undertake at least once in their lifetime. For a traveler far from home, knowing the precise direction to Mecca, known as the Qibla, was essential for performing daily prayers correctly. The astrolabe could determine this direction by calculating the Great Circle route from the user's current location to the coordinates of Mecca, a complex spherical trigonometry problem solved mechanically by the instrument's clever design. This transformed the astrolabe from a scientific tool into a deeply personal object of faith, guiding the devotee not just through the hours of the day, but also orienting their spiritual focus toward the center of their religious world. The pursuit of horological excellence in the Islamic world was not limited to portable devices. It also manifested in grand, public displays of engineering prowess that built upon the ancient tradition of the water clock. Islamic engineers took the basic clepsydra and transformed it into a spectacle of art and automation, designed to inspire wonder and demonstrate the ruler's command over time and technology. These monumental clocks, often installed at city gates or in royal palaces, incorporated elaborate automata moving figures, ringing bells, and rotating displays that activated on the hour. The most famous example is the elaborate water clock gifted by the Abbasid Caliph Harun al-Rashid to the Holy Roman Emperor Charlemagne around 807. While the original is lost, contemporary descriptions describe a marvel of bronze craftsmanship, where mechanical knights emerged from doors to mark the hours and tiny horsemen circled a dial. This artistic and technical zenith was achieved in the 13th century by the brilliant engineer Ismail al-Jazari, whose Book of Knowledge of Ingenious Mechanical Devices is a breathtaking catalog of his automata and clocks. His most celebrated timepiece was the elephant clock, a towering synthesis of cultural and engineering knowledge. A meticulously crafted elephant carried a howdah, or pavilion, on its back, which housed a complex water clock mechanism. Every half hour, the intricate machinery would spring to life. A figure in the howdah would raise a mallet to strike a cymbal, a bird would whistle, and the elephant's driver would tap a drum. The entire sequence was not just a time signal but a philosophical statement, representing the fusion of different world traditions: the elephant from India, the dragon from China, the phoenix from ancient Egypt, and the automata from Greece, all working in harmonious synchrony under the umbrella of Islamic science. These clocks were more than machines. They were kinetic sculptures that celebrated the orderly and wondrous nature of Allah's creation, making the invisible passage of time a visible, audible, and awe-inspiring public experience. Yet another layer of this cosmic theory emerges when we consider the game's profound spiritual stakes. The ball game, or obelisks as the Aztecs called it, was far more than a simple sport. It was a ritual reenactment of a foundational creation myth. In Maya mythology, the hero twins, Hunahpu and Xbalanque, famously journeyed to the underworld, Xibalba, and defeated the lords of death in a ball game, a victory that preceded the dawn of the current era of humanity and the resurrection of their father, the maize god. Playing the game was therefore a way to participate in this eternal cycle of death and rebirth, a story intrinsically linked to the sun's own daily journey into the darkness and its triumphant return at dawn. The hard rubber ball, soaring through the air, could be seen as a physical representation of the sun itself, battling against the forces of darkness, its movement a microcosm of the celestial struggle that sustained the universe. This interpretation is powerfully reinforced by the game's often brutal conclusion. Historical accounts and artistic depictions, particularly from the classic Maya period, make it clear that the game could culminate in human sacrifice. While the exact reasons are debated, a prevailing theory suggests the losers, or sometimes even the winning captain, were offered to the gods. This grisly finale takes on a chilling new meaning when viewed through the lens of the timekeeping theory. If the ball represents the sun, then its final stop at the end of the game, whether through a goal or the symbolic death of a player, could represent the sun's sacrifice at the end of the day, a necessary offering to ensure it would be reborn the following morning. The court, in this view, becomes more than an observatory. It transforms into a sacred theater where the most vital cosmic drama was periodically staged and resolved by human actors, directly linking the fate of the community to the eternal, ticking clock of the heavens. But if the courts of Mesoamerica were theaters of cosmic drama, the temples of ancient Egypt offer a different kind of celestial map, one carved not for a bouncing ball, but for eternity in stone. High on the ceiling of a chapel dedicated to Osiris within the vast temple complex of Hathor at Dendera lies one of the most captivating and debated artifacts from the ancient world, the Dendera Zodiac. This breathtaking bas-relief is not a simple decoration. It is an intricate circular diagram, a snapshot of the heavens that has fascinated and perplexed scholars since it was first brought to light during Napoleon's campaign in Egypt. To modern eyes, it looks instantly familiar, a wheel of constellations, including the Ram of Aries, the Bull of Taurus, and the Twins of Gemini, all circling a central pole. But to assume it is merely an ancient star chart is to miss the profound and layered purpose behind its creation, a purpose that sits at the mysterious intersection of precise astronomy, deep mythology, and potent ritual magic. The first challenge in understanding the zodiac is its date. The temple at Dendera was constructed during the Greco-Roman period, but the celestial knowledge it represents is far older, a fusion of pharaonic Egyptian tradition and the Babylonian zodiac system that had spread across the Mediterranean world. The relief itself is a detailed planisphere, a representation of the night sky. It depicts the constellations of the zodiac, the 36 decans, star groups that rose consecutively to mark the hours of the night, and the 5 planets known to the ancients, all orbiting around the North Celestial Pole. This alone suggests a sophisticated understanding of the cosmos. Yet, this is not a scientific diagram in the modern sense. The figures are not plotted with geometric precision. They are rendered in the classic Egyptian artistic style, with gods and goddesses embodying the celestial bodies. The constellation we know as Orion is represented by the god Sa, while the star Sirius is the goddess Sopdet, forever chasing him across the stone sky. This immediate blend of the accurate and the allegorical tells us that the Dendera zodiac was never intended to be a practical guide for a sailor or a farmer to navigate by. Its audience was priestly, and its context was undoubtedly religious. So what was its purpose? One compelling theory is that it served as a grand, permanent reference for liturgical timekeeping. The Egyptian temple was a machine for maintaining cosmic order, or ma'at, and its rituals had to be performed at exactly the right moment to be effective. The rising of certain stars and constellations heralded the arrival of specific hours of the night and key moments in the calendar. like the imminent flooding of the Nile. The Dendera zodiac, fixed permanently on the chapel ceiling, could have provided the temple's priests with a visual key to these cycles. By knowing the date and comparing it to the positions on the carved sky, they could determine which decan was rising and therefore which rituals needed to be performed to keep the universe functioning smoothly. In this view, the zodiac was a crucial component of the temple's infrastructure, a stone instruction manual for ensuring the sun would rise again and the cycle of life would continue. However, another layer of interpretation points towards a more esoteric function, deeply intertwined with Egyptian beliefs about the afterlife and the journey of the soul. The chapel that houses the zodiac is dedicated to Osiris, the god of the underworld and resurrection. In Egyptian funerary texts, the deceased soul is described as traveling through the sky, becoming one with the circumpolar stars that never set, the so-called imperishable ones. The central figure on the zodiac, around which all the constellations turn, is not a mathematical point but a depiction of the jackal-headed god Set, holding up the pole. This is not a neutral scientific symbol, it is a potent mythological image. For a soul navigating the perils of the afterlife, this map could have served as a spiritual guide, showing the path to eternal life among the stars. The zodiac, in this sense, becomes less a timekeeping device and more a symbolic gateway, a promise of salvation carved in stone for the god Osiris and, by extension, for the pharaoh who was his earthly embodiment. The most likely truth is that the Dendera zodiac was all these things at once, a testament to the Egyptian mind's ability to weave together observation, myth, and ritual into a seamless whole. It was a representation of the sky, yes, but it was the sky as the Egyptians understood it, a divine realm where the movements of the stars were the actions of gods, where time was a sacred cycle to be maintained through ceremony, and where the ultimate destiny of every soul was written in the heavens. It wasn't a question of whether it was astronomy or astrology. For them, these were the same discipline. To measure the sky was to understand the will of the gods, and to depict it was to participate in its eternal order. The Dendera zodiac is therefore more than an ancient artifact. It is a window into a complete worldview, where science served faith, and the entire cosmos was a temple waiting to be read. Ultimately, the steady rhythm of these ancient clocks did far more than just mark the hours. It synchronized the very heartbeat of civilization, weaving the fabric of society itself. By mastering the ability to predict the seasons, early cultures unlocked the potential for stable agriculture, the absolute bedrock of any complex society. No longer did communities have to guess when the life-giving floods of the Nile would arrive, or when the first frost would descend on the fields of Mesopotamia. With a reliable calendar, farmers could plan the entire growing cycle with confidence, knowing precisely when to sow, tend, and harvest their crops. This predictability led to massive food surpluses, which in turn supported population growth, allowed for labor specialization, and freed people from the constant, desperate struggle for daily sustenance. For the first time, not everyone had to be a farmer. This surplus of food and time empowered the emergence of artisans, soldiers, merchants, scribes, and priests, creating the diverse and interconnected economic landscape that defines a thriving civilization. The ability to keep time accurately was, in the most literal sense, what made cities possible. This control over the calendar also became the ultimate source of political and religious authority, a power almost exclusively held by a privileged priestly class. In societies from Egypt to Mesoamerica, the ability to read the heavens and declare the correct date for a planting season or a religious festival was seen as a divine gift, a direct line to the gods. The ruling class, often a fusion of king and high priest, wielded this knowledge to demonstrate their indispensable role as the mediators between the human and the celestial realms. They could literally make the sun stand still, in a ceremonial sense, by predicting an eclipse or orchestrating a solstice alignment at a grand temple. This created a powerful feedback loop. The priesthood's predictions ensured agricultural success, which reinforced their authority and justified their elevated status, wealth, and control over the population. To control time was to control the people, as the calendar dictated not only farming, but also the scheduling of taxes, military campaigns, and labor for monumental construction projects, cementing the ruler's power in both the spiritual and the administrative spheres. On a more intimate level, shared timekeeping rituals forged a powerful sense of cultural identity and communal belonging. When an entire city gathered to witness the sun's rays illuminate the inner sanctum of a temple on the equinox, or when a village participated in a new fire ceremony marking the end of a 52-year cycle, these were not mere spectacles. They were profound, collective experiences that bound individuals together, reinforcing a shared worldview and a common set of values under the auspices of the state religion. These calendrical ceremonies provided a stable, predictable rhythm to human life, offering comfort and order in a world that could often seem chaotic and threatening. The calendar told people not only when to plant but also when to celebrate, when to mourn, and when to seek the favor of the gods, creating a social framework that guided human activity from birth to death and connected each individual's life to the grand, eternal cycles of the cosmos. Perhaps most importantly, the relentless pursuit of temporal accuracy became the engine for groundbreaking scientific discovery. The need to refine the calendar and understand celestial motions drove the development of advanced mathematics, precise observational astronomy, and surprisingly sophisticated engineering. Babylonian priests, intent on perfecting their predictions, developed complex arithmetical systems to model the irregular motions of the planets. Greek artisans, inspired by these astronomical problems, pioneered early gear technology and mechanical engineering, culminating in marvels like the Antikythera Mechanism. Chinese astronomers, tasked with maintaining the emperor's mandate of heaven, compiled meticulous records of celestial events that remain invaluable to scientists today. Each failed prediction, each slight drift of the calendar, presented a new puzzle to solve, pushing the boundaries of human knowledge and technology. The quest to build a better clock was, fundamentally, a quest to understand the very mechanics of the universe, proving that the drive to measure time has always been inseparable from our deepest desire to comprehend our place within the cosmos. For all their astonishing successes, the ancient quest to capture time was also a story of profound frustration, heartbreaking loss, and systems that collapsed under the weight of their own imperfections. We must remember that for every enduring calendar or ingenious device, there were countless others that failed, drifting into obsolescence and dragging the societies that depended on them into confusion. The history of timekeeping is not a straight line of progress. It is a tapestry woven with threads of brilliant insight and unraveled by human error, political meddling, and the sheer, daunting complexity of the cosmos they sought to measure. Consider the cautionary tale of the Mayan calendar round, that magnificent 52-year cycle created by the interlocking of the Tzolk'in and the Hab. While it was a masterpiece of cyclical thinking, it contained a built-in historical amnesia. Because the system reset every 52 years, any event that occurred more than a lifetime ago became impossible to place uniquely on a longer timeline. A date like 4can5 pop would recur every 5 decades, making it hopelessly ambiguous for recording a deep, linear history. This is precisely why the Maya were forced to develop the long count, to escape the limitations of their own brilliant but temporally shallow creation. Their earlier system, for all its ritual perfection, was a failed tool for historians, a lesson in how a calendar designed for one purpose can be utterly inadequate for another. This struggle was even more starkly visible in Rome before Julius Caesar's intervention. The pre-Julian calendar, manipulated by politicians for personal gain, had become a symbol of a state failing in its most basic duty, to tell its citizens what day it was. The pontiff's power to arbitrarily insert the intercalary month turned time itself into a political currency, creating a society that was chronically out of sync with the natural world it relied upon. Farmers couldn't trust the dates for sowing, merchants couldn't plan for journeys, and the entire rhythm of public life was subjected to the whims of a few powerful men. This wasn't just a failed system, it was a broken one, a vivid demonstration of how the abstraction of time, when poorly managed, could corrode the very foundations of an empire. And then there is the knowledge that was lost entirely, leaving behind only tantalizing fragments that hint at a sophistication we can scarcely imagine. The Antikythera Mechanism is the most poignant symbol of this tragedy. That one miraculous device, salvaged from the seafloor, forces us to confront a terrifying historical truth. The vast majority of ancient scientific and technical knowledge has vanished without a trace. The mechanism was not a magical anomaly. It was a product of a technological tradition. The understanding of gear trains, differentials, and astronomical modeling required to create it did not spring from a vacuum. It implies workshops, textbooks, teachers, and apprentices, an entire ecosystem of advanced mechanics that has been almost completely erased from the historical record. We are left with this one exquisite fossil, while the species that created it remains a mystery. How many other Antikythera mechanisms were melted down for their bronze, or decayed into dust, taking their secrets with them? The silence of history is deafening, reminding us that progress is not inevitable and that dark ages can indeed descend, swallowing centuries of innovation. This constant struggle highlights the fundamental challenge our ancestors faced: the task of measuring an abstract, continuous flow using concrete, imperfect tools. A sundial is useless without the sun. A water clock's flow changes with temperature and water purity. A candle clock burns differently in a draft. Every single method was a compromise, a negotiation with the physical world to yield up its secrets. They were trying to capture a river in a box made of sand, to cage the sun with a shadow, to count the infinite with the finite. Their story is not just one of triumph, but of relentless, humbling perseverance in the face of a concept that never stops, never repeats exactly, and never fully reveals itself. Their failures are as much a part of their legacy as their successes, a testament to the audacious human spirit that refused to stop trying to read the clockwork of the universe. This profound legacy is not some distant, abstract history. It is ticking on your wrist and flashing on every screen in your home right now. Those ancient civilizations did far more than just invent clever gadgets. They built the very architecture of modern time, an invisible framework so deeply embedded in our lives that we rarely stop to consider its ancient origins. Every time you casually agree to meet a friend at 7:30 or glance at a calendar to see that it's April 12th, you are participating in a tradition that stretches back thousands of years, a direct inheritance from the priest astronomers of Babylon and the sun-worshipping architects of Egypt. Our most fundamental time unit, the 24-hour day, is a gift from the Egyptians, who loved to divide things into 12, just as they divided their daylight hours with their towering obelisks. The concept of splitting that day into two 12-hour periods, AM and PM, is a direct descendant of their solar observations. But what about those 60 minutes in an hour and 60 seconds in a minute? We owe that entire structure to the Babylonians and their fascination with the number 60, a sexagesimal system that proved so mathematically elegant for division that it was adopted by Greek astronomers, preserved by Islamic scholars, and eventually etched onto the very first mechanical clock faces in medieval Europe. The reason your clock face is a circle of 360 degrees, and your hour has 60 minutes, is because a Babylonian mathematician, thousands of years ago, looked at the sky and saw a perfect circle that was best divided in this way. Our calendar is an even more direct line to the ancient world. Take a look at yours, that 365-day year, with its 12 months of roughly 30 days each. That is the undeniable legacy of the Egyptian civil calendar, later refined and adopted by Julius Caesar to create the Julian calendar, the very backbone of the system we use today. The names of the months themselves: July for Julius Caesar, August for Augustus, are Roman imprints, while the 7-day week has roots in Babylonian astrological traditions, each day dedicated to one of the 7 celestial bodies they observed. Every single date you write down is a testament to this long, unbroken chain of human observation and calculation. even our relentless drive for greater precision, which has culminated in the atom-splitting accuracy of atomic clocks that define a second by the vibration of a cesium atom, is part of the same story. It is the ultimate extension of that ancient desire to pin down the elusive flow of time, to move from the macro to the micro, from the sweep of a shadow to the oscillation of a subatomic particle. The atomic clock did not replace the ancient quest. It fulfilled it, achieving a level of accuracy that would have been pure magic to the builders of Stonehenge or the designers of the Antikythera Mechanism. They laid the foundational concepts. We simply found ever more precise ways to measure them. This invisible thread connects the stone circle to the satellite, the water clock to the smartwatch. When your phone automatically adjusts for daylight saving time or syncs to the network's atomic clock reference, it is the endpoint of a journey that began with humans gazing up at the heavens, searching for order in the movements of the sun, moon, and stars. They gave us the framework, the hours, the days, the years. We filled it with digital precision, but the underlying architecture, the very grammar of time we speak every day, is their enduring gift. It is a humbling reminder that our hyper-connected, technologically advanced world still runs on rhythms first discerned by ancient eyes staring at the night sky, finding in the chaos of the cosmos the first, beautiful notes of a universal clock. Looking back across this incredible journey, the sheer diversity of human ingenuity is nothing short of breathtaking. From the silent, sweeping shadow of an Egyptian obelisk to the intricate gearwork of the Antikythera Mechanism, from the celestial mathematics of Maya cycles to the polarized light navigated by Viking sailors, every culture, in its own unique way, reached for the heavens and the earth to solve the same fundamental problem. They used water and stone, sand and stars, bronze and belief to build bridges across the endless river of time. This wasn't merely a technical pursuit. It was an expression of something deep within us, a profound need to find order in the cosmos, to mark our place within the grand cycle of existence, and to ensure our survival, our rituals, and our societies moved in harmony with the universe itself. This quest to quantify time is one of the oldest and most defining chapters in the human story. It sits at the beautiful intersection of science, spirituality, art, and power. It gave us the stability to build cities, the precision to navigate oceans, and the framework to organize our lives. The echoes of these ancient innovations are not confined to history books or museum displays. They are alive in the very seconds, minutes, and hours that structure our modern world. Every time you check your watch or glance at a calendar, you are participating in a tradition crafted by countless generations of curious, brilliant, and determined people who simply looked up at the sky and wondered how it all worked. As we bring this exploration to a close, we're left with a deep sense of admiration for the creativity and perseverance of our ancestors. Their legacy is a powerful reminder that the drive to understand our world is what ultimately propels us forward. So now we'd love to hear from you. After learning about these astonishing ancient clocks, from Stonehenge's stone calendar to China's hydraulic marvels, from the Inca's Golden Sun Temple to the Maya's cosmic cycles, which one captures your imagination the most? Which method do you find the most fascinating or ingenious? Share your thoughts and favorite moments from history's greatest clocks in the comments.